Hi, my name is Maria Carroll, and today we will be talking about facial recognition algorithms.
This presentation is based off the paper Eigenfaces versus Fisherfaces, Recognition Using Class-Specific Linear Projection. What is face recognition? A facial recognition system is a computer application which uses algorithms to identify a face from a digital image. This is used by police stations, customs services at airport, and U.S. Department of State in visa processing. However, it's not always very accurate. Variations in lighting, facial expression, and the angle between the face and the camera can all cause these algorithms not to work very well. Also, different things about your appearance change from day to day, like whether or not you're wearing glasses or your hairstyle. This paper had two goals. First, they wanted to develop a facial recognition algorithm, which they call Fisherface, that is insensitive to lighting variations and facial expressions. The second goal of this paper was to compare the algorithm's accuracy and runtime to other currently known facial recognition algorithms. We're going to talk about four facial recognition algorithms: correlation, Eigenfaces, linear subspace, and Fisherfaces. Correlation uses the nearest neighbor classifier in the image space. You normalize each image in the test and learning sets to have a zero mean unit invariance, then assign each unknown image the label of the closest point in the learning set, where distances are measured in image space. Basically, you take all of the images in your learning set and decide which image looks closest to your test image. There are a lot of disadvantages with correlation. Variation in light conditions leads to a loosely clustered image space. For accuracy, we need a learning set with a densely sampled continuum of all the possible lighting conditions that may occur on this test set. Correlation is computationally expensive, and you need large amounts of storage. The second algorithm we're going to talk about is Eigenfaces. This uses principal components analysis to maximize the scatter of all the projected samples. And here's the math behind it. It's your basic standard PCA. The biggest advantage of Eigenfaces is that it runs faster than correlation and uses less memory. However, there are several disadvantages. Scatter is not only maximized between the classes, but also within the classes. This makes the Eigenfaces algorithm even less accurate than correlation. Most of this in-class scattering is due to light variation, and it can be minimized by discarding the three most significant principal components. However, this may also lead to loss of information, which actually helps facial discrimination. The third algorithm we're going to talk about is linear subspaces. In the linear subspace algorithm, we recognize that a face is a Lambertian surface. Lambertian means that it is a diffusely reflecting surface, like your skin. This means that all images of the face lie in a 3D linear subspace of the high dimension image space, regardless of lighting conditions. With three images of a face under three known linear independent light source directions, we can discover the albedo and surface normal of each point on the face, which allows us to reconstruct the image under any arbitrary lighting condition by a linear combination of the original three images. So, how does this work? When we look at the image, we only know one thing: how much light is being directed back at the camera. If we happen to know the light source, which is S in this equation, then we can calculate the albedo and the normal vector if we have three linear independent photos with three S's. Once we determine the albedo and surface normal of each point on the face, we can reconstruct the image under an arbitrary lighting direction by a linear combination of the three original images. So there are several advantages and disadvantages of linear subspaces. First of all, linear subspaces are insensitive to a wide range of lighting conditions while only requiring three learning set images, so that's good. It's also very, very accurate. However, self-shadowing, specularities, and facial expressions give the face variability that the linear subspace model doesn't handle very well. This can be remedied by increasing the size of the learning set, which determines which part of the face are likely to vary. The linear subspace algorithm is computationally expensive and memory intensive. Now this brings us to the last algorithm, Fisherfaces, the one that was invented for this paper. Fisherfaces uses the same technique in regards to Lambertian surfaces as linear subspaces. It It recognizes that the variation within each class lies in a linear subspace of the image space. It follows that the classes are convex, and thus linearly separable. It performs dimensionality reduction while retaining linear separability and uses Fisher's linear discriminant. So here's the math behind it. We have two scatter matrices this time, a between-class scatter matrix and a within-class scatter matrix. When we maximize the determinant of the total scatter matrix, our goal is to increase the distance between classes and decrease the distance within classes. So there are several advantages of Fisherfaces. First of all, FLD achieves greater between-class scatter than PCA, so this simplifies the classification. It's faster than linear subspaces and uses less memory. It's also more accurate than correlation and eigenfaces. There are two experiments in this paper. The first experiment used variation in lighting, and the second used both variation in lighting and facial expression. In the first experiment, there were 5 different people, and they each had 66 photos taken of them with different lights. Each photo had one light source, and we broke it into 5 different subsets depending on how severe the lights were on their face. So if you look at these photos in subset 1, the light's coming straight at you, and where at subset 5 it's very much coming to the sides. So in the first part of this experiment, we used subset 1 as the training subset and tested its accuracy on subsets 1, 2, and 3. In the first test, we see that they all do very well when you use both the subset 1 for training and testing. However, when we get to more and more lighting differences, Eigenface and correlation perform very poorly, while linear subspace and Fisherface do pretty well. In the second example, we train on subsets 1 and 5 and test on subsets 2, 3, and 4. And once again, we see that Eigenface and correlation don't do very well, whereas Fisherface and linear subspace do pretty well. In the second experiment, we have differences in lighting and facial expression. It was tested on full headshots and closely cropped faces. Our different pictures include faces with glasses, ambient light, 3 points of light from different angles, and 5 different facial expressions. This paper also looked at a comparison of principal components for the Eigenface algorithm. We see that the more principal components we have, the better our error rate becomes. This test was performed by a leave-one-out method. What they did was take all of the photos of all 16 people and take one photo out, and that is your test photo. Then, all of the other ones are in the learning set. When they did this, they found that all the algorithms were more accurate when using the full face rather than the closely cropped face. However, the paper recognized that this probably won't hold in real-world applications because people's hairstyles have changed their profiles, which is part of what the algorithm was using to figure out who the person was. We see that introducing changing facial expressions now causes the linear subspace method to have pretty poor results. Fisherfaces, however, holds its own with a 7.3% error rate. The Fisherface algorithm can also be used to determine if a person is wearing glasses. PCA was also investigated with to see if it could recognize if someone was wearing glasses. In this test, they had 2 different classes, people with glasses, people without glasses. The PCA error rate was 52%, and considering that there's only 2 options, either wearing glasses or not wearing glasses, it didn't work at all. The Fisherface algorithm, however, had an error rate of only 5%. In this paper, there were a number of lessons learned. All methods examined in this paper perform great if the test image is similar to the training images. The Fisherface method performed the best for variations in lighting and facial expression. Removing the largest 3 principal components improved the performance of the Eigenface algorithm, but it is still not as good as Fisherface. More principal components in Eigenface give us performance closer to correlation. Performance appears to level off around 4 to 5 components. The linear subspace method performed excellently for lighting variations, but could not handle facial variations. The Fisherface algorithm seems to work amazingly well. So why is facial recognition so hard today when this paper was written 15 years ago? These experiments had every participant facing directly towards the camera. In these experiments, we had many samples for very few people, where in real life we could be trying to match a face from a database of millions of people and probably not have 30 samples of each person under multiple controlled lighting conditions. Also in real life, people wear different glasses, have changing hairstyles and facial hair, and sometimes wear makeup, all of which these algorithms just really don't handle very well.